Hey, let's say you're a big fan of Cody Bellinger and you get a chance to go to a Dodgers game and you really want to catch one of his home run balls. And you know that Cody Bellinger hits home runs by this spray chart. And there are two questions that you're asking here. One is if you want a Cody Bellinger home run ball, you do not sit in left field. You sit somewhere in right field. But where exactly would be your best opportunity? And the other thing is how far up in the stands do you want to sit? How far away? Because some home runs are closer and some are further. And so to optimize your chances, you need to pick the center of this distribution, but then there's what would be called a payoff, which is the distance that home run got hit. And these are two things that we can calculate from a distribution using integration. And so that's what we're going to be. Just to get the vocabulary down, this is called the mean. That would be the mean home run. Some home runs are really mean, I know, especially when the other team hits them late in the game. And this is the expected value of the distance. So you need both of those if you're going to catch one of these home run balls. And also a mitt. Okay. So let's remind ourselves about distributions. Distributions are functions that they're strange. Usually, in practice, the distribution function is only covering a finite part of the plane. There's one big exception to this, and the distribution function is always positive. And if we're going to call it S, then the integral from a to b of s of t dt is 1. Well, that's easy, okay. So that kind of makes it hard to figure out whether something's a distribution. You have to integrate it and see if you get 1. If you get 2, you just divide it by 2, and that gives you, then the integral is 1. So that's the area, because the distribution function is always positive, and the integral is 1. And we also know that if you take a situation where you look at the integral between x0 and y0, I don't know why I picked those letters, but I did. The area there is the integral from x0 to y0, and that's the proportion of the observations that fall between x0 and y0. Everything's kind of backwards with this, so it's not where it happened. Where it happened is the observation, not what did you see when you got there. Okay, so if we look at Cody here, what we're seeing here is a sample. If you gave Cody a million at-bats and sampled them, then this would be that sampled spray chart, but actually it would be some nice smooth function like this that we're trying to get at. It's a passive function. We can't really get at it, but that's the best we're going to do. Okay, so first let's talk about the mean. And the mean is it goes back to kindergarten. You know, everything that you ever needed to learn about integration, you learned in kindergarten. You don't believe that, do you? Okay. So here's what you learned in kindergarten. If you sat on a seesaw or a teeter-totter or whatever it is that you call it, and if you had a 40-pound weight 5 feet, say, from the fulcrum, and you wanted to balance that, that would have to be a 20-pound weight 10 feet from the fulcrum. So those balance. So it's the weight times the distance, the weight times the distance. Physicists call that distance the arm, and there'd be torque or moment based on it's the weights of force times the arm. And so that's what we saw. Those are how those things are going to balance out. Okay, so what happens here now, if we wanted to sample and get at the mean of these things, what we're trying to get at is kind of the arm, and so what we're going to do is we're going to subdivide the domain as we usually do for integration. And then we're going to do some samples. So we're going to take a sample of S, but we need the distribution, that would be the weight distribution on the teeter-totter, and the arm. So we have to sample both S and the distance. So we have two samples there. And in each little sector, the total contribution, the moment, is in that example, it's the angle or whatever it is. So it's x sub I times s sub I times delta x. So remember that to get the right units on the distribution, you have to multiply by the horizontal units, and so that's what we're doing there. And so there's the moment, and so we would add up those little moments. There's lots of little moments. Those are great home run moments. These are ESPN moments. No, different use of the word moment. Add up all the moments, and that would give us an approximation to the actual something, the actual mean, and that's an integral. We recognize that as not being the integral of s of x. That's the integral over the whole domain of x times s of x dx. So that's the mean. And it's, I've said before, sometimes it's the choosing of the samples that's the tricky part, and I think that's what's happened here. Because you have to realize for the problem at hand, you need to sample both the distance and the distribution, and then multiply by delta x to get an actual number. And so there it is. So there's the mean, and that's pretty cool. I'm taking advantage of the fact that most of the time when we do this, the domain is finite. It goes from A to B, and that means that in principle you would have to go from minus infinity to infinity, and so those are improper integrals. But in practice, it's just from A to B. Okay. So that would give, if you did this with the Cody-Bellinger function, that would give you I would imagine somewhere around here, that would be where to sit if you want to catch a home run ball. And so, but now you need to know what the distance is. So the distance is like a payoff, and so it has an expected value. That's the technical term. It's a little bit harder to see with this situation. So I want to take a single die. That, remember, dice is plural for die. And so we're going to, I don't remember exactly how the pips go, but we've just got a cube with some pips on it, and we roll it. And we're going to play a game, and the game is this. If you roll a 3 or 6, you get $4. And if you roll anything else, you get $1. So, and you have to pay $3 to play this game. So a third of the time you win, 2/3 of the time you lose, and so those are the parameters. This is really an abstract model of what's going on here. So, so what happens here is you do this a bajillion times, and a third of the time you get $4. And so let's just say it's 3,000 times. So 2,000 times you get $1, and 1,000 times you get $4. And so what you expect to get over 3,000 plays is 3,000 times, it's 4/3 plus 2 times 1/3. So that's the expected value, EV. So you do 2,000 of them. 2/3 of them would come out not 3 or 6, so you'd get $1, and so that would be $2,000 that you get, and a third of them would come out to be $4. That's $4,000 that you get, and then you would add up all the money you got and divide by 3,000 to get a per play situation. Well, that's what's going on with these distances for these home runs or for other kinds of things that are described by distribution. You get a payoff. Some things are worth more than others, and so you're valuing, in that dice case, the threes and the sixes more than the other rolls, but this could happen with anything else where you have a number attached to each possible outcome. So you want to get the expected value of that number. And so what we're going to do is subdivide the domain. And now, instead of sampling the distance, well, we need to sample the distribution so we know how many things are in there. But instead of sampling the horizontal component, we're going to sample the payoff. And so the samples now are going to be the home run distance. Distance is an awkward thing in calculus because it starts with D, and we always use D for something else. So I'm going to call that P sub I. So that's a sample payoff in each sector. And S sub I is the sample distribution. And the estimated payoff for a small sector would be P sub I times S sub I times delta X. So S sub I times delta X is the number of things that are in that sector, and you get P sub I for each of those. Or it could be the proportion, and you get P sub I for each of those. So this is a lot like the mean, but instead of sampling where you are along the domain, you're sampling the payoff at each point along the domain. And so you add those up, and you take the limit. These are cases where we really do take the limit, and we recognize that this is the integral from a to b of p of x, that's the payoff function, times s of x dx. And that's the expected value. And it's used quite commonly in statistics and other applications. This is what you expect to get out of doing whatever it is. Now, in the Cody-Bellinger case, this tells you which section of the stadium to sit in and how far up to sit. And good luck, and I'll autograph that ball for you when you catch it.